Hey there, it's Ken the Metal Professor. I'm going to run through a few examples of plotting rational functions. This is an extension of a conversation I was having with one of the people I've been working with about this topic, and I'm just going to put it there for public consumption. I'm also doing a little experiment here with the video. I have two video streams going into the computer at the same time. One for my document camera, hi, and one is the normal webcam so that you can see my smiling face while I'm doing this. So I'm going to work through a progressively updating version of kind of the same core problem. So I'm going to start with this function, this rational function, which remember is a function that's a ratio of two polynomials. And we're going to graph the heck out of this thing and do it in a way that we can minimize the need to plot any individual points whatsoever by building the skeleton for the graph and then filling in some details that will help us decide what has to be happening. And you'll see what I mean as we progress. Now I'm going to assume that you can factor things, so I'm going to skip over the factoring and get to the end result here in just a second. But before that, I want to emphasize that right off the bat, you can decide something about this rational function. And again, I'm assuming that you have a little bit of background with this so that if I start talking about slant asymptotes or horizontal asymptotes, and then also vertical asymptotes, you know what the heck I'm talking about. By now, if you're looking at this, you've probably seen enough of these problems to recognize that you can confirm whether there might be a horizontal or a slant asymptote on a rational function's graph just by looking at the degrees of the polynomials in the numerator and the denominator. And these degrees are the highest power of x that appears. And the rule is that if the degree of the numerator is equal to the degree of the denominator, you're going to have a horizontal asymptote. If at a non-zero value of y, if the degree of the numerator is less than the degree of the denominator, the x-axis is going to be the horizontal asymptote. And if in the special case where the degree of the numerator is exactly one more than the degree of the denominator, you're going to have one of those lovely slant asymptotes. So this particular one is going to have a slant asymptote. Now I'm looking around for something that I can block the image with a little bit here. I'll try this. So here's how you can think about that. There are fancy procedural algebraic ways to really dig out a slant asymptote, but here's a more loose way you can think of it. Slant asymptotes and horizontal asymptotes are telling you what's going on as you go farther and farther out on the x-axis to x equals 10, 100, 1,000, a million, billion, and negative 10, negative 100, negative a billion, right? So when we are getting out to super huge values of x, the terms that really take things over in the numerator and the denominator are the leading terms, the 2x cubed and the x squared. Because if I'm at x equals 1,000, this negative 2 in the denominator, and maybe even this plus x in the denominator, they're insignificant compared to the x squared. And similarly in the numerator, if x is like 47 billion, then x cubed is certainly going to be a much larger value than 8x squared and 6x. So to think about a slant asymptote, what you can do is just kind of start thinking about as the importance of these trailing terms diminishes. What does this function end up behaving like? Well, as the importance of those trailing terms diminishes, this function behaves more and more like 2x cubed over x squared, which simplifies to 2x. And that is why you get a slant asymptote on the line y equals 2x. It's also why, if you pretended for a moment that this numerator had a lead term of x squared, that going through that same exercise of ignoring the trailing terms as their importance diminishes, if this numerator was 2x squared, then what's left over would balance out to just 2. And that's why you would have a nice flat asymptote at y equals 2. Okay, so right off the bat, before any work at all, this particular function is going to have a slant asymptote of y equals 2x. So we've already determined that before we proceed. Now, proceeding to look at the numerator and the denominator in factored form. In that numerator, you can see hopefully that there's a 2x available to factor out. And then having factored out the 2x in the numerator, that's happened here, that leaves behind two quadratics, which I designed to be easily factorable. Okay, and we get here, and oh, looky there. It looks like because there's a common factor in the numerator and the denominator, that x minus 1, algebraically speaking, those would cancel. Now, this is an important feature on the graph as well, because the presence of this x minus 1 term right here, well, and back here and up here, tells us that we are never allowed to use x equals 1 on this graph. Because in the way the function was originally posed, plugging in x equals 1 would put a 0 in the denominator. Not allowed. Even if there's a 0 in the numerator. Too bad. Okay? Now this means that we're going to have a hole in the graph at x equals 1. We can't plot that point. It's not an asymptote because we've just taken whatever this graph is and we've plucked out whatever point would have happened at x equals 1. And so still, before a whole lot has happened, we've already discovered a slant asymptote and a hole in the graph. And then the final version of this function, simplified, is 2x times x minus 3 over x plus 2. This gives us more information. Because of the history of this function, we know that we're not allowed to use x equals 1. In the final simplified form, we see, you know what, we could plug x equals 1 into that. Now, that doesn't mean that we can go replace that point in the curve because that point was gone from the very beginning, where we were not allowed to use x equals 1. It's not in the domain. However, this tells us that if we could use x equals 1, what would the value of the function want to be? It would want to be 2 times 1 times negative 2, so negative 4 over 3. All right, and so that gives us basically a thumbtack on the graph of this function, except when we're done, we're going to put a little hole there because we're not allowed to use that point on the curve. I see my focus is going a little out because I think I have autofocus on and I'm not going to stop and try to fix it just yet. Hopefully it won't get too bad. When I'm done with this problem, I'll lock it in place. All right, so now we have to get to work plotting this thing. Does this mean we now have to start plotting a bunch of points? No. There's other parts of the skeleton that we can determine, and particularly from this, there are 3 other really good pieces of information. There's going to be a vertical asymptote at x equals negative 2. Okay? The problem with x equals 1 got algebraically taken away, leaving behind a hole in the graph. But problems with x equals negative 2 are going to persist, and we can't get rid of those. It's not surgically removed from that graph. We also know from the numerator that the value of the function is going to be 0 when x is 0 and when x is 3. Those are from the numerator. Right? So we have a whole bunch of stuff here. There, the slant asymptote, the hole in the graph, and vertical asymptotes and x-intercepts already in place. And I'm going to argue that this is going to allow us to graph this curve without technically plotting any other points. Now, we are going to have to think about some things. So here's what I'm going to recommend. I'm going to draw a number line. And I'm going to put on this number line markers for each of these important features that we've seen at this tail end, the vertical asymptotes and the x-intercepts. And I'm going to put them in order. So negative 2 is the first important marker, 0 and 3. Those are where something changes on the graph. We hit a vertical asymptote, so the function breaks, like somebody took scissors and clipped it. And x-intercepts are where the graph changes from positive to negative or negative to positive. Or perhaps comes up, touches the x-axis, and goes back down, something like that. But we know it's a thumbtack that goes in where we know where the graph is going to be. I'm going to determine in between these locations whether the graph needs to be positive or negative. And we can use this simplified form for this. So for x values less than -2, the structure of this function, when x is less than -2, provides a negative value for x, a negative value for x minus 3, and a negative value for x plus 2. Because numbers from down here, when we add 2 to them, the result is still negative. So the structure of the function is a negative times a negative over a negative, and altogether the graph wants to be negative. In between -2 and 0, the structure of this function is a negative times a negative over, now it'll be a positive number in the denominator. The net result there is the value of the function will be positive. Between x equals 0 and x equals 3, we'll have a positive number, because now we're greater than 0. X minus 3 will still be negative. And in the denominator, we're taking x and adding 2. So if x is already positive, positive there, altogether, the value of the function is going to be negative between 0 and 3. And then after 3, everything is positive, and we get that. So now we know whether the graph is going to live above or below the axis. Now, how do we know it's not going to have any other changes amongst those places? Well, if there were going to be places where we change from positive to negative, then we would have found an x-intercept at that location, and we don't have any more. So this is what we know. All right. Now, I'm going to take away this page, and I'm going to start drawing some good stuff. And I'll slide the page in as needed to show things. So here are my axes. Okay, what do I know? Well, I know that I need a slant asymptote of y equals 2x. So I'm just going to kind of, there we go. It's kind of steep. So there's my slant asymptote that eventually I will follow. Now, the secret to slant asymptotes is the graph can actually cross the slant asymptote in the center here more than once. It just means that as we go farther and farther out, the graph is going to come in for a landing along that line, even though we might actually cross it here or there in the central core part of the graph. We can't cross vertical asymptotes, but we can cross horizontal asymptotes and we can cross slant asymptotes, because those just tell us what's going on way, way, way out. Let's see, what else do we need? I might as well put in this stuff. I need a vertical asymptote at -2. Okay, so here's my vertical asymptote. And then I need x-intercepts at 0 and 3. So I know that those are points the graph of this function will have to go through. And I know, remember, that there's going to be a hole in the graph at x equals 1, y equals -4/3. So right about there. Okay, and I'm going to fold my paper here. Let's not forget this information. When I'm to the right of x equals 3, the graph needs to be up here. When I'm in between 0 and 3, the graph needs to be down here. And when I'm in between 0 and -2, the graph has to be back up here. And then over here, the graph has to be down there. Now, how can I make this happen while I'm playing nice with the vertical asymptotes? Over here, got to be up here, down here, up here, and then here's a vertical asymptote. So it looks to me like the graph can be positive, then negative, and then positive just by doing this. Now, what you're not seeing here is that farther out off the paper, that slant asymptote and this graph are getting closer and closer together. What about the rest of it? Well, I need to the left of -2, remember, the graph has to be negative to the left of -2, but it needs to follow this horizontal asymptote and this slant asymptote, so perhaps it does this. Now, how do I know that this piece of the graph isn't up here? Maybe it does this, right? Maybe it follows the slant asymptote. Well, it can't do that and come up here because, first of all, it needs to be negative everywhere to the left of -2. But also, if the graph did do this, there would have been an x-intercept. And there isn't, because we found them all before we even started graphing this. Okay, so that is my anticipation of what the graph of this is going to look like. Now I'm going to pause a little bit and pull up a good graph of it and take a look. Okay, so here was my pretty awful sketching of what this graph ought to look like. This little wiggle, I could have drawn it a little bit more smoothly. The placement of my points is estimated, but it should be pretty close. All right, so now I'm going to pop up what the graph of this thing really looks like. Now, first of all, I'm going to show it kind of close up, sort of. It's close in on the x-axis, but not the y-axis. So now you can see the same behavior, right? Here's the x-intercept at 0. Here's the x-intercept at 3. Here at x equals 1, what should be -4/3 is that hole in the graph, right? Now, I drew more of a wiggle here than it looks like there actually is, but that's okay. We don't see the hole in the graph because, well, first of all, I told, this is Maple. I told Maple the simplified version. So number one, Maple wouldn't know to put a hole in the graph. And even if I gave it the original version, the resolution of the screen wouldn't allow for you to see one little pixel being skipped, right? So the hole in the graph is not really something that's going to show up. We just have to know it's there. Now I'm going to stretch out the x-axis and stretch down the y-axis and up a little bit so that you can really see this this slant asymptote behavior here in the vertical asymptote. So here's the large scale vertical asymptote at x equals -2. And so this right here is sort of the start of that slant asymptote. Now again, remember, I had the behavior down here in pencil. You could see sort of a downward facing umbrella. And we're seeing that in a properly scaled picture. It's looking a little bit more wide than mine is. But here, let's go back to x equals -50 and out to x equals +50 and see what happens here. Now we can see. Now you can really see that slant asymptote taking over as we go farther and farther out. And again, recognize our function does cross what turns out to be this slant asymptote here in the middle, but that's okay. Slant asymptotes are cool. They're to be crossed in the center core of your graph. Asymptotic behavior is telling you the story about what's going on way farther and farther and farther out. The interior shenanigans of any crossings doesn't matter. Crossing a vertical asymptote is bad news. Okay, so there we go. That's graphing a rational function with pretty good detail in it. I had to plot 1 point. Well, okay, technically I plotted 3 because I also plotted x-intercepts, but those are easy, right? I've also taken up almost 20 minutes doing this, so I'm going to pause again and prepare another example. That one I'm going to go through lickety-split, when hopefully it will make a lot more sense given what we've done here. Okay, back with example number 2. Very quick break for you, but a lot of preparation for me. So here is a second example of plotting a rational function, and this time I'm going to go through the results a lot more quickly than the first one. The original form of the rational function is there, 2x cubed minus 8x squared plus 6x over x squared plus 3x plus 2. You might recognize that that numerator is exactly the same as in the other example, but I've changed the denominator to add a little more dynamics. So right off the bat, without any other ado, we can decide whether or not there's going to be a horizontal or a slant asymptote here. Same story as the first problem. There is going to be a slant asymptote at y equals 2x, right? Now, with that determined, we can probably factor this thing. We should be able to. And there is the result. Again, same numerator as the previous problem, but a different denominator. The difference here is we're not going to see a hole in the graph. We've traded a hole in the graph for a second vertical asymptote. And in fact, we can see that information right away. From the denominator, we will have vertical asymptotes at -1 and -2. From the numerator, we will now have x-intercept at 0 and at 1 and at 3. Okay, now this gives us a skeleton for our graph. I'm looking for what I did with it. Oh, I think it's on the other side of this page. I'll show it to you in a second. Let's prepare, besides the skeleton of asymptotes and x-intercepts we have here, let's take a look at where we expect this graph to be positive and negative. I've done exactly the same thing as before, where I just made a number line with the key x values where behavior changes. Either we break the graph to go over a vertical asymptote, or we have an x-intercept, which tells us that if we're not crossing the x-axis from negative to positive or vice versa, at least we're going to touch it there. I've put all those markers on a number line, and then in between each of those pairs of values, I've used the factored version of this function to tell me whether I expect the values of the function to be positive or negative in those zones. And so, for example, in between -2 and -1, I would have a numerator with a negative number, and a negative number, divided by a negative number and a positive number, because if I'm to the right of -2, when I do x plus 2, I'm going to get a positive result. Now that's 1, 2, 3, 4 negative signs and a positive sign altogether. That's going to be positive. And then you can see the rest of the zones. Pause this and try them out just to make sure you agree if you want. But negative to the left of -2, negative between -1 and 0, etc., etc. So far, so good. All right, so then here is a badly drawn set of coordinate axes. Here, I'll do better. I'll put an arrow. There's an x-axis. There's the y-axis. I've drawn on a dashed line, which is supposed to approximate the slant asymptote. Ignore the fact that it looks like it's bending down here. We've got the two vertical asymptotes at -2 and -1, and we have the three x-intercepts at 0, 1, and 3. I've also marked in pinkish color the sign behavior, SIGN, that we expect for our graph. So, can we figure this out? In this zone out here, this positive is supposed to be over there a little bit. So we need a graph that's positive in this zone, negative in this zone, positive in this zone, but then negative back here. And by the time we get to this zone, we have to be obeying this vertical asymptote. Now remember, in the center, we can cross this slant asymptote, no problems. Okay, so is it possible and relatively easy to get something that's positive here, negative here, positive here, and then come over here and obey this asymptote? And remember, we have to go through these 3 points, right? Well, I think so. And also off the screen, right, this slant asymptote is heading up in that direction. Once we cross x equals 3, the function is positive and needs to stay positive all the way out. So we know that way out there, the graph is going to be heading up towards that slant asymptote. So then it could come down here, cross into negative territory, go back across the axis here, back into positive territory. Now again, the slant asymptote we don't really care about right now, but we do know we have to turn over and come back to this x-intercept, and then we have to become negative, and then we also have to follow that vertical asymptote. Okay, so that's what the graph kind of sort of looks like there. Now, in this zone between -1 and -2, there are no x-intercepts, and the graph has to be positive, and it has to obey the asymptotes. We can't cross them. So the graph has to be positive everywhere between -1 and -2. It can't cross the axis, or we would have found more roots, but it also can't cross these vertical asymptotes. So really, the only thing it can do is something like this. It's obeying the asymptotes, but it's staying positive. Okay? And then for the graph out here, the graph to the left of -2, we want the function to be negative. So we've got to be down here, but we have to obey this asymptote and also this asymptote. So up here, we can't draw it here, because if we drew it on this vertical asymptote, then right in this area, then if it follows up this asymptote, looks like it's going to cross the axis again and become positive, and that can't happen. So the only way for this to fit is to do that. Okay. So quite a lot of dynamics to this graph. Now, this is a very badly drawn by hand approximation. Here is a close-up of, well, I guess I can't call it a close-up because the y-axis is going down to -100. This is a view that shows us a bunch of the dynamics in there. You can see here to the right of the axis, the graph comes up positive, goes down negative, and goes up positive again. Let me zoom in. Let's do that. Okay, so what we were seeing here, a bump positive, below negative, and then up to positive again, is actually demonstrated right there. And then the graph just falls off far down below along that vertical asymptote. Now everything else disappeared because I zoomed in, so let's zoom back out a bit. Now we're seeing this part of it, this lower left segment of the function, right? That is this piece. Wow, well, where the heck is that stuff in the middle? It's gone. Well, maybe I need to go up farther on the y-axis. Let's go up to 50. Oh man, there's still nothing there in the middle. Let's go up to 100. Oh man, still nothing in the middle. Is something wrong? And no, I mean, there have to be points there. So let's take y up to 200. Ah, there it is. So finally we found it. So remember, my badly drawn piece of the graph showed up right here in the same kind of horizontal spread as the rest of it. As it turns out, the values of this function in this little stretch between x equals -1 and x equals -2, they don't start until up over y equals 100. But we got the dynamics properly in our badly hand-drawn. Notice I've changed it to our badly hand-drawn map instead of my badly hand-drawn map of this function. But here's Maple doing a much better job. And I really have to go back into Maple and figure out how I can zoom in and out by rolling my mouse, scrolling on the mouse. I used to be able to do that, and I don't know how to do it anymore, and that bothers me. But anyway, just to get a quick feel of how this thing ought to work, doesn't take very long. A bit of factoring, identify holes, slant asymptotes, vertical asymptotes, x-intercepts, decide whether the graph needs to be positive or negative between some of those markers, and then figure out how that can happen. And then if you need to get more careful placement, like of this piece here, then okay, maybe you need to come back to this and plot a couple of points, like go to x equals -1.5 and get the value of the function to see just how far up this has to go. But at least you can get a sense of what's going on. All right, since I've been at this for half an hour now, I'm not going to work a third problem all the way through. I'm going to suggest that you do a little practice if you're interested. So here is another variation on the two functions we just saw. What I've done here is taken this term in the denominator that would have been just x minus 1 in the previous example or two ago, and I turn it into x squared plus 1. What that does is it makes the degree of the numerator 3 if we multiply all this out, 2x cubed plus a bunch of other stuff, and in the denominator, the degree of that is now 3. X squared times x cubed plus a bunch of stuff. This tells us that as x gets bigger and bigger and the other stuff becomes less and less significant, this function wants to behave more and more like 2x cubed over x cubed, or just 2, which tells us that this graph is going to have a horizontal asymptote at y equals 2. And then from this factored version of the function, we can learn other things. There's a hole in the graph at x equals 1, because this term in the denominator factors, right, into x minus 1 times x plus 1, and then that x minus 1 cancels up and down like in the first example. You could go back to this version of the function, not that version. If you went and canceled the x minus 1s and wrote down sort of the final reduced version of this function, you could get an idea of what y coordinate that hole would want to sit at. Vertical asymptotes at -1 and -2. Here, let me write this down just to be safe. The numerator looks like this. The denominator, when it's totally factored, looks like this. The x minus 1s cancel, right? So that's why there's a hole in the graph at x equals 1. The y value at that point would be 2 times 1 times -2 divided by 2 times 3, so -4/6. After this x minus 1 has canceled, we see the two terms that will generate the vertical asymptotes at x equals -1 and x equals 2, and we see the surviving terms in the numerator that will give us our x-intercepts at x equals 0 and x equals 3. So now you can draw a number line and assess whether the curve needs to be in the positive or negative territories to the left and right of each of the crucial points, being the vertical asymptotes and the x-intercepts. And then having done that, you can slap together what ought to be a reasonable graph of this function that has the right trends in the right places. And if you want to put it in exactly the right spot, then you're going to have to plot some extra points. But that whole plotting of individual points can wait until way, way down the line when you're trying to get a graph of these things. So I hope this helped help you get your head around the information that's available in a rational function to help you somewhat painlessly, it's all relative, right, but somewhat painlessly set the skeleton for the graph and put all the pieces in the right places.